Now, these represent the molecular formula. It cannot provide you any information about the structure it shows.
Yes.
You have seen alum in a solid state crystal. Potash alum is a white crystal.
Yes.
Potash alum is a colorless crystal. It has potash is plus, aluminum is 3 plus, sulfate is 2 minus.
Yes.
So 3 plus 1, 4 plus. So there are 2 sulfate. Have you understood?
Yes.
Okay. What is the coordination number of potassium ion? Aluminium?
6.
So, the octahedral structure. So 6 water molecules surround the potassium ion and aluminium ion in an octahedral fashion. Similarly, 6 water molecules surround the potassium ion octahedral.
Yes.
How many potassium are there?
2.
How many potassium are there? 2. So 12 water molecules.
Yes. Yes.
How many aluminum are there? 2. 12 water molecules. So 12 plus 12 makes 24.
Yes. Yes.
So the water molecule is not water of crystallization. Water molecules are coordinated water molecules. The water molecule forms a coordinate bond through oxygen. What is the structure of water? Isn't it this one?
Yes.
Oxygen has 6 valence electrons. Out of 6, 2 are used to form a bond with OH. And the remaining 4 are present in the form of 2 lone pairs.
Yes.
And one of the lone pair is given to the metal to form a coordinate bond, that is a sigma bond.
Yes.
So the water molecule, each water molecule is acting as a Lewis base, is acting as an electron pair donor, and occupies the corners of an octahedron. And that is why it has an octahedral structure. The sulfate ion, the sulfate oxygen, forms a hydrogen bond The structure is stabilized due to this. The sulfate oxygen forms hydrogen bond with coordinated water, which are present along aluminium as well as surrounding potassium ion. And that stabilizes the crystal structure of alum. So in the crystal, the 6 water molecules are surrounding potassium in an octahedral fashion. 6 water molecules are surrounding aluminium in an octahedral fashion. And the sulfate oxygen is forming a hydrogen bond with the coordinated water molecule. When you dissolve in water, when you dissolve it in water, the structure is vanished. No octahedral structure remains. It gives you potassium ion, aluminium ion, and sulfate ion. No hydrogen bonding, no octahedral structure. The structure collapses when you dissolve it in water. But in solid state, the structural identity is retained. The octahedral structure is shown only in the solid state. As soon as I dissolve, the structure vanishes and you see only the potassium ion is present in the solution, aluminium ion is present in the solution, and the sulfate ion is present in the solution, but no preferred geometry is shown. Whereas coordination complexes, they retain the structure both in the solid as well as in the solid solution. So, there are 6 ammonia molecules within the secondary sphere, within the coordination sphere, so it will show octahedral structure.
Yes.
This compound, it shows octahedral structure both in solid as well as in solution. So that is the difference between an alum, a double salt, and a coordination complex. Coordination complex retains its identity in solid as well as in solution.
Yes.
But double salt shows its structure in solid but loses in solution. So in solution the structure is lost. Whereas in coordination complex, both solution and as well as solid will show the structural identity.
Yes, sir.
Excuse me, sir. Sir, how is that hydrogen bonding done between that H2O and SO4 dinegative?
Who is asking me? I can't see the person. Can you come forward? Who is okay? Here.
Sir, how is that hydrogen bond formed between that H2O and SO4 dinegative? How is it possible?
First of all, oxygen is more electronegative than hydrogen.
Yes, sir.
So the bond is polar covalent bond.
Yes.
The wedge bond is polar covalent. So already there is some delta positive charge is developed on hydrogen. Now, when it coordinates to the metal, This electron is lost from oxygen because
Yes.
oxygen has given a pair of electrons to the metal.
Yes.
So the electron deficiency is increased now from minus to 2 minus. Now oxygen is more electronegative than hydrogen. So it will pull the electron cloud between OH bond toward itself, making H as H delta plus more.
Yes, sir.
So the coordinated water, the hydrogen of the coordinated water is more positively charged than the normal hydrogen in the water molecule. Because in normal water, there is no pull by the metal. Whatever is there due to OH electronegativity difference, the polarity is developed. But this polarity is further enhanced due to electron donation to the metal. Since the metal is accepting an electron pair from oxygen, so the oxygen becomes electron deficient.
Yes.
Is it
Yes,
clear?
Yes, sir.
Yes, sir.
Since oxygen is electron deficient, so oxygen is more electronegative than hydrogen. So the electron pair between OH bond will be shifted more towards oxygen to
Yes.
compensate the electron deficiency of oxygen. As a result, hydrogen will be more delta plus.
Yes.
Greater the delta plus character, stronger is the hydrogen bond between highly electronegative atom like oxygen, fluorine.
Yes, sir.
Is it clear?
Yes.
Yes.
Yes, sir.
Excuse me, sir. Sir, how is the structure of these coordination complexes, like amorphous or crystal? Sir, how is the structure of these coordination complexes? Like amorphous or crystal?
Both. If you precipitate the compound quickly, you get an amorphous variety. But if you allow slow evaporation, then the crystals are formed.
Excuse me, sir. So the structure of the coordination complex remains same in solution. So is it that they are insoluble in water because there is no dissociation?
No, coordination complexes can be of both types. It could be soluble in water, it could be insoluble in water. You can't say generalized coordination complexes. Some complexes are water insoluble, some complexes are water soluble. So what was your question?
So
I
in case of
can't
water-
see who is the person? No. Bolo.
So in case of water soluble complexes, the structure will not be retained in the
Structure,
the structure will not be retained in the solution.
structure will retain. It is only the solvent present, that's all. The structure
So, but-
is
There will be
What
no
is that?
dissociation.
no. If the complex is stable, there will be no dissociation. The condition is the complex must be stable to retain its identity in solution as well as in solid. If the complex is not stable, then it will dissociate and the structure will not be retained in solution. But if it is stable, there will be no dissociation and the structural identity will be retained both in solid as well as in solution. So water has nothing to do about dissociation. Water simply gives the medium to get it dissolved, that's all. Solvent acts as a medium. It does not encourage the dissociation.
Yes.
Yeah.
So in a single structure of potash alum, two molecules of SO4 dinegative are able to satisfy K positive and Al tripositive. So why do we need two atoms each of K, Al and H2O in the entire structure of a double salt?
Because when you prepare double salt, you start with potassium sulfate, aluminium sulfate, dissolve it in water, and then evaporate the solution. And then you get this alum structure. Is it clear to you now?
Yes.
Potassium sulfate is sodium.
Yes.
Excuse me, sir. So, what factors determine the stability of a coordination complex?
Stability of coordination complex. Who is the boss? You. Okay. Stability of the coordination complex depends upon the metal ion, depends upon the group with which it is attached, on both factors. So you cannot just generalize that which will give stable, which will not give stable. Transition metal complexes are in general stable, whereas non-transition metal complexes are less stable than the transition metal complexes. But if you compare NiCl4 and nickel and platinum, you just see the periodic chart. They are in the same group or not?
Yes, sir.
Anion is common,
Yes.
nickel is 2 plus, because 4 negative charge,
Yes.
2 positive charge by potassium, so nickel has to be 2 plus.
Yes.
What is the oxidation state of platinum?
2+2.
As you go down the group, the reactivity decreases. So you see, it is not so easy to discuss about the stability. It depends upon what type of metal, what type of ligand it is associated with. If I compare chloride versus cyanide, cyanide is an accepted type ligand. So it gives a metal ligand interaction is stronger. So it will be more stable than the NiCl4 2 minus. So it depends upon both on the metal as well as on the group with which it is attached.
Yes.
Okay, now we will classify the complexes. Coordination complexes can be classified into 3 categories: cationic, anionic, and neutral. When an anion is present outside the coordination sphere, That represents the ionization sphere.
Yes.
So when anion is present in the ionization sphere, that is outside the square bracket, then it represents a cationic complex. That means the charge on the complex
Yes, sir.
if the charge of the complex is not positive, then why do we need an anion? What is the role of anion? To neutralize the charge?
Charge.
Yes.
Yes.
So if anion is present outside the coordination sphere, that indicates that this charge on the complex is positive.
Positive.
And if the charge is positive, that's a cation. All cations have positive charges.
Yes.
You can see here the anion is present outside the coordination sphere.
Yes.
In this case, the cation is present in the outside the coordination sphere. Sodium ion, potassium ion, they are in the ionization sphere. If the cation is present in the outside the coordination sphere, that means the charge on the ion complex is negative.
Yes.
And when neither cation nor anion is present, then it is neutral. Chromium 3 plus, 3 chloride ion gives 3 minus. So there is no charge on the complex. So it's a neutral complex.
Yes.
So the complexes can be classified into 3 categories. Cationic complex, anionic complex, and a neutral complex. Neutral complex can be differentiated from cationic and anionic easily. Can you suggest me a method by which technique I can use to distinguish neutral from cationic or anionic complex?
No ionization sphere exists.
Ionization.
Measure the conductivity.
Yes.
There is no ion present, so it will be a non-conductor, whereas this will be a conductor. So anionic and cationic complex will be conducting because the ions are present. You have chloride ion, you have the complex ion. You have complex ion, you have chloride ion. You have potassium ion, you have complex ion. So you have cation and anion, both cationic and anionic complex. But in neutral complex, there is no charge on the complex. So what is the charge in this case? What is the charge on the complex in this case?
Minus 2.
2 minus. What is the charge on this complex? That is why I need 3 sodium ions to neutralize the 2 negative charge. To neutralize the 2 negative charge, I need 2 potassium ions. So if the cation is present outside the coordination sphere, it's an anionic complex. If anion is present outside the coordination sphere, a cationic complex. Neither cation nor anion, it's a neutral complex.
Excuse me, sir. Sir, you told that the coordination complexes retain their shape even in their solutions. Then how that free ions are present for conduction?
Because the anion, which is the chloride ion, is not forming a coordinate bond. It is satisfying the primary valency of the metal. It behaves like a free ion. Whereas this chloride is different from this chloride. How do you know? Because this chloride is forming a coordinate bond. So it is satisfying primary as well as secondary. This is only primary. So one which is satisfying only primary behave as a free ion. Okay? Now I will tell you an example. I will give you an example. If we look, the molecular formula is the same. 1 cobalt, 5 ammonia, 1 chloride, 1 sulfur. In this case, the chloride is within the coordination sphere, sulfate is in the ionization sphere. In this case, sulfate is in the coordination sphere, chloride is outside the coordination sphere, that is ionization. If you add silver nitrate, you will get a white precipitate of silver chloride.
AgC. Yes.
But if you add silver nitrate here, no precipitate. That shows that when the anion, the same anion, is present within the coordination sphere, behaves differently than when it is present in the ionization sphere. So in the ionization sphere, it will give the same chemical test like free ion, whereas in the coordination sphere, it will not respond to the chemical test. Similarly, if I add barium chloride, no precipitation.
Yes.
But if I add barium chloride, white precipitation. So what is the difference? Difference is one is forming a coordinate bond, another is not forming a coordinate bond. The one which forms a coordinate bond does not behave like a free ion, so it does not respond to the individual chemical test. Whereas when the anion is present outside the coordination sphere, they behave like a free ion, they respond to the individual chemical test. Is it clear?
Yes, sir. Yes, sir.
Now, what is ligand? Ligand What is the minimum condition for a group to function as a ligand? So, a group can be a ligand only when there is at least one lone pair of electron present on the atom itself, which forms a coordinate bond to the metal when they are present within the coordination sphere. And when they form a coordinate bond, that is the sigma bond. The ligand to metal donation is a sigma bond. When ligand gives a pair of electrons to the metal, it forms a sigma bond. What is the characteristic of a sigma bond?
Higher electron density on the line joining the nuclei.
Good. When the electron densities are increased between the two nuclei, along the internuclear axis, the electron density has been enhanced.
Yes.
That gives a sigma bond. That's a head-on collision. The overlap is head-on.
Yes.
So when px overlaps, what do you get? So you have increased the electron density along the internuclear axis. And that is a characteristic of a sigma bond. What is a pi bond? The lateral overlap.
Lateral overlap.
Because of the lateral overlap, along the internuclear axis there is no electron density, so it represents the node. Okay. Now, ligands can be classified into three categories. Ligands could be classified into three categories. Sigma donor and a pi donor, sigma donor and a pi acceptor. In one case I have written pi, another case I have shown the symbol. They are both same. Okay? What is common? What is the common in all cases? That means all are giving a pair of electrons to the metal. So that is why they are sigma donor. Ammonia molecule, the nitrogen has 5 valence electrons. Because nitrogen is a 15th subgroup, so there will be 5 valence electrons.
Yes.
Out of 5, 3 valence electrons are used for 3 NH bonds.
Yes.
So there will be a lone pair available on nitrogen.
Yes.
It forms a coordinate bond to the metal by giving a pair of electrons from nitrogen to metal. Why the ligand has to give electron to the metal? Because metals are normally electron deficient. Metals are all normally positively charged. If the atom is positively charged, that means it is electron deficient. It has less electrons, so its odds for accepting electron will be high. So the ligand, it will accept the electron from the metal ligand to form a coordinate bond. Why we call coordinate bond? What is the difference between a covalent bond and a coordinate bond?
There is a of the lone pair. Equal. Equal. Unequal.
When each gives one electron, then you fall a covalent. When one atom is giving both the electrons, it's a coordinate bond. So ammonia is a sigma donor ligand. Ammonia does not have any other lone pair to available to act as a pi donor. It does not have any orbitals to accept the electron from the metal, because nitrogen is a second period element. And in case of second period, the maximum covalency is 4. So it has only one lone pair of electrons, so it can only give a pair of electrons to the metal. It does not have a vacant orbital to accept the electron from the metal, so it cannot act as a pi acceptor. Neither it does have any extra electron pair to function as a pi donor. But, so ammonia is a sigma donor ligand. If I take NH2 minus, nitrogen has how many valence electrons? Nitrogen has how many valence electrons?
5.
And one extra negative charge. So 6. Out of 6, only 2 are used to form NH1.
Yes, sir.
So NH2 minus will have 2 lone pairs of electrons.
Yes.
One will be forming a sigma bond to metal, and if necessary, another can form a pi bond to the metal.
Yes.
So what is the minimum requirement for the second category? At least 2 lone pairs of electrons.
Yes.
One for the sigma, another form a pi bond if necessary. If necessary, not always, but if necessary, it should be able to form a pi bond.
Yes.
Water, you see, water has 2 lone pairs.
Yes.
Yes.
OH minus. Oxygen has 6 valence electrons,
Yes.
and the negative charge gives another electron. 7. Out of 7, only 1 is used to form OH bond. So there are 3 lone pairs available.
Yes.
Yes. Halide. 7 plus 1, 8 electrons. Halogen group has 7 valence electrons. So the halide will have 8 valence electrons. So 4 lone pairs will be there. So you see, all of them can function as a sigma donor as well as pi donor if necessary.
Yes.
But ammonia can act only as a sigma donor and nothing else.
Yes.
Pi acceptor all are sigma donor and pi acceptor. Carbon monoxide we have discussed in metal carbonyl that it first gives a pair of electron and then accepts the electron from the metal to its antibonding orbital.
Yes. Yes.
Plus CO, NO plus, they are all isoelectronic. Are they isoelectronic or not?
Yes, sir.
Carbon monoxide 4 plus 6, 10.
Yes.
Cn minus 4 plus 5 plus 1, 10.
Yes.
NO plus 5 plus 6 minus 1
Minus
10.
Yes.
All of them have the same number of valence electrons. So they are isoelectronic. They are isoelectronic to what?
Into
Nitrogen, which is 5 plus 5 gives 10. Each of them have lone pairs and they function as a sigma donor by giving a pair of electrons to the metal, and they accept the electrons from the metal to its antibonding orbital, 2p pi star orbital, except here where the metal electrons enter into the vacant 3d orbital. Phosphate, alkyl or aryl phosphate. Alkyl, while R is the methyl group, ethyl group, that is alkyl phosphate. I told you that this is phosphine. Just like ammonia. In place of a nitrogen, you have phosphorus. It is called phosphate. When the hydrogen is replaced by the alkyl group, it's alkyl phosphine. When it is replaced by the aryl group, it is aryl phosphate. Both will be a pi acceptor ligands. And which accepts electron is a Lewis acid. Which gives electron is a Lewis base. Which accepts electron is a Lewis acid. So, that is why I have written pi acceptor or pi acid ligand. The ligand which accepts the electron from the metal are called pi acceptor or pi acid ligand. This one,
Excuse me, sir. So these ligands will accept the electrons from the metal in their anti-bonding pi star molecular orbital. So, it would instead to destabilize them, no? These ligands. So how are they stabilized by accepting electrons from metals?
metal carbon constant in physics. Metal carbon constant in physics. CN bond state decreases. What is happening? The metal carbon bond becomes a double bond character and C triple bond O becomes a double bond character. So the CO bond is weakening. The metal carbon bond strength is strengthened. That is why the complex becomes more stable.
Yes.
So, what is the specialty? Anybody who has any question to ask? Okay. Why I said cyanide is a special type? Because cyanide is the only one which has a negative charge. You see all other cases, neutral, 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 nitrogen, neutral, here positive, but in this case it is negative. Because of its negative charge, it has excess electron.
Yes.
So it is electron rich. Because it is electron rich, it can stabilize the metal in high oxidation state. It also stabilizes metal in low oxidation state. It shows a dual peak. For example, quickly tell me, what is the oxidation state of nickel?
Zero.
4 cyanide gives 4 negative charge. 4 potassium gives 4 positive charge. So what is the oxidation state of nickel?
Zero.
What is the oxidation state of iron?
Plus 3.
So you can see yourself, the same ligand can stabilize both higher as well as lower oxidation state. Whereas these only will stabilize the lower oxidation state of the metal. Because they are neutral, because they are either neutral or positive charge, so they are less electron, density is less, So it can stabilize only the metal when it is electron rich to give the electron back to the ligand.
Yes.
So when it stabilizes higher oxidation state, its role is more as a sigma donor. When it stabilizes the lower oxidation state, its role is more as a pi acceptor. So it shows a dual behavior that sometimes it stabilizes the higher oxidation state because it's a good, better donor of electron because of its negative charge. And it stabilizes the lower oxidation state because it acts 2pi antibonding orbital is free, so it accepts the electron from the metal, so stabilizes the metal in a low oxidation state. Except cyanide, all other will stabilize only the metal in the low oxidation state and not high oxidation state. Whereas these two type ligand, sigma donor or sigma donor and a pi donor ligand, will stabilize metal in high oxidation states. So sigma donor and pi donor, they will stabilize because they donate electrons. So they can neutralize the electron deficiency of the metal in a high oxidation state. So they stabilize the high oxidation state. This requires the back donation from the electron from the metal. So since it accepts the electron from the metal, so the metal must be electron rich condition. And the metal is electron rich when it is in a low positive oxidation state.
Yes.
So that's all about today's lecture, okay?